What's going on, guys? Let's look at this problem right here. Here this question is asking identify the type of differential equations such as separable, linear, Bernoulli's, etc. Let's look at the first one. The first one says 3 plus y sin x dx is equal to cos x dy. And this is linear and exact. I'm going to show you how it is. So first of all, you have to know the linear pattern. For linear differential equation, the pattern will look like this. We will have dy by dx plus we will have a function of x, p of x, multiply by y, that will be equal to another function of x that will be q of x or something. You can name anything you want. Okay, now let's see whether we can bring this one into this pattern. Here we have dy, we have to bring dy by dx. So we bring this dx to this side. In that way we will have 3 plus y sin x, that's equivalent to cos x dy by dx. Okay, now we have dy by dx. Now in front of dy by dx we shouldn't have anything, so we have to bring this cos x to the other side. So this is going to be 3 over cos x plus y sin x divided by cos x, that's equal to dy by dx. Okay, now the next thing is this has to be addition of a function of x multiplied by y. So here which one is the function of x multiplied by y? This one is the function of x multiplying with y, right? So we have to bring this one in this side. If we bring that one, let me use a different color. If we bring this one to this side, this is going to be dy by dx, and this is going to be minus, and sin x over cos x, that's going to be tan x. So this is going to be tan x y, and that's equivalent to 3 over cos x. 3 over cos x, we can write it as 3 sec x. 3 sec x. So from this one you can see this is this pattern, dy by dx plus function of x multiplying y, that's equal to another function of x. So this is linear. Now let's see how we can prove this is an exact differential equation. Now to prove this one exact, let's get rid of this thing. Okay, let's get rid of this thing. And to prove this one exact, you have to know the exact pattern. Whenever you have exact differential equations usually come in two patterns. One of them is m of x comma y plus n of x comma y dx over dy is equal to 0, or you will have something like this, m of x comma y dx plus n of x comma y dy, that's equal to 0. So if you have any of this pattern, and after you derive this pattern, you have to see the derivative of this one with respect to y, and derivative of this n of x comma y with respect to x, not this dx is not included. Without that, we only look at the function, and we take the derivative of this one with respect to y, derivative of this one with respect to x, and see whether these two are equal. If these two are equal, then this is exact. Okay, now I'm going to get rid of this one because I want to bring into this pattern, so I need some space. So let's get rid of these things. Now let's try to bring this one into that pattern. So first we have to equalize everything to 0. Here we have 3 plus y sin x dx minus cos x dy, that's equivalent to 0. So this is matching one of the pattern. One of the pattern, if you notice, we have a function of m of x comma y multiplied by dx and n of x comma y multiplied by dy, that's equivalent to 0. So this is matching that pattern. So after we bring into this pattern, what we have to do is we have to take the derivative of this m with respect to y and see whether it is equivalent to derivative of this n with respect to x. Okay, so this is our m of x comma y function. We are going to see the derivative of y, derivative of this one with respect to y is going to be equivalent to derivative of that one with respect to x. So let's go ahead and take the derivative of this one with respect to y. If I take the derivative of this one with respect to y, we treat x as a constant, so we only take the derivative of y. Y is going to be what? If we take the derivative of y, that's going to be just 1. And this is going to be just, and 3 will become 0. So y sin x will turn into just sin x. And here we have, if we take the derivative of n of x with respect to x, derivative of cos x is negative sin x, but here we have to take the negative also, because if you look at the pattern we saw before, I write the pattern again so you can see it clearly. So this is the pattern we had, like m of x comma y dx plus n of x comma y dy, that's equal to 0. So here we have a plus, but here we have a minus, so we have to include that minus in this function. In that way, if you take the derivative of this cos x, that's going to become negative sin x. So negative negative cancels each other, we will get a sin x. So these two are equal, therefore this is an exact differential equation. And that's how we prove a differential equation is exact or not. Okay. Now let's look at the next one. Here we have dy by dx is equal to xy plus 5x minus 2y minus 10 over xy plus 3x. This is not like direct, straightforward, but this is a separable differential equation. I'm going to show you how to find it out. So whenever you have something complex like this, you can simplify, you can try to simplify or factor. If you have any situation like this, try to do that first. So from that you can realize whether it's separable or not. Now here, that's what I'm going to do. Dy by dx. Separable mean what? We can separate y terms to one side and x terms to the other side. Well, let's see whether it's possible. Here, if you look at this one, here we can take the x common in the first one. So if we take x common, this is going to be what? Y plus 5. And in the second one, if I take negative 2 common, this is going to be y plus 5. And in the denominator, we can take the x common. That's going to be x times y plus 3. Now, whenever we have situation like this, we can also write this one. This is equivalent to x minus 2 times y plus 5. And in the denominator, we will have x times y plus 3. And in the other side, we have dy by dx. Now let's see whether we can separate this y and x terms together. Now it's very clear we can separate. Now let's go ahead and do that. Okay. So this is going to be y plus 3, and in the denominator we will have y plus 5, and that one multiplied by dy. In the other side we have x minus 2 divided by x multiplied by dx. So now you can see y terms are in the one side and x terms are in the other side. So this is a separable differential equation. Okay. Now let's look at the next one. Here we have xy plus x square y power 2 over 3 dx plus x square dy is equal to 0. Now this is Bernoulli's, and also this is homogeneous. Now it's easy to prove this is homogeneous. For homogeneous, what we have to have is all the power must be equal. Xy, what is the power? 2, right? X square times y, and then power 2 over 3. You can think it in two different ways. Like you can add these two together, like 2 times 1, 2 and 1, that's 3. And if you multiply 2 over 3 times 3, that's going to be just 2, right? 2 is what we want. And then here also 2. So this is a homogeneous differential equation. Now to prove this one, Bernoulli's differential equation, in Bernoulli's what we have to have is, we have to have a linear pattern. In linear differential equation, we will have dy by dx plus p of x times y, that's equal to another function of x. But in Bernoulli's, addition to this one, we will have a function of y, power will be not equal to, like, that will be not equal to 0 or 1. It should usually greater than 0 and 1, something like that. Now let's see whether we can, sometime it will be a fraction. Let's see what we get from this one. Okay. If we rearrange this one, xy plus x power 4 divided by 3, and then y power 2 divided by 3 times dx, and dx is common for both, so let's keep it as it is. And in the other side we have x square dy. So first we have to have a function like these are equal to 0. Now first we have to bring a dy by dx pattern. So in order to bring that, I move this x square dy to the other side. In that way we will have xy plus x power 4 divided by 3 y power 2 divided by 3 times x times dx is equal to negative x square dy. Now here we have a dx. If we bring this dx to the other side, that's going to be in the denominator. So we will have xy plus x power 4 divided by 3 y power 2 divided by 3, that's equal to negative x square dy by dx. Now after we derive this one, the next thing is we have to have an addition of function of x multiplying y. Now which one is a function of x multiplying y? If you look at this one, this is the matching term, right? We have to have a y power 1 like addition of this one. So that's gonna be dy by dx negative x square, and if I bring this one to this side, that's gonna be negative xy, and that's equivalent to x power 4 divided by 3, y power 2 divided by 3, and also we have to get rid of this negative x square, so you just have to divide this side by negative x square. If you do that, let's continue here. So this is going to be dy by dx minus xy, and if I bring this, I have to divide this one also by negative x square, and then if I bring this negative x square to the other side, I'm dividing everything by negative x square to bring the general pattern, like we have to have nothing in front of this dy by dx, so that's why I'm dividing everything by negative x square. If I divide, I have to divide this one too, and in that way we will have x power 4 divided by 3, y power 2 divided by 3, and then divided by negative x square. Okay, now you can see here we have dy by dx without this y power 2 over 3. This is a linear pattern, dy by dx plus function of x times y, that's equal to another function of x. We have that one without this y square divided by 3, y power 2 divided by 3. So whenever you have something addition y power something not equal to 0 or 1, that's a Bernoulli's differential equation. Okay, that's how we prove. Now let's look at another example. Here we have dy is equal to 3 plus e power 3x minus 4y plus 6 times dx. So this is linear substitution. What makes this one linear substitution? Because this is not Bernoulli's, this is not separable, this is not exact, so you cannot do anything. Why it is not anything? Because of this e power. So whenever you have something like this is a linear substitution. So what you have to do in this kind of problem is you have to equate this one to another variable. For example, you have to equate this one to v, 3x minus 4y plus 6, and you have to rearrange this one in terms of y, and you have to find out dy by dx, and instead of all the y, you have to replace this one with v, and then you have to solve this one. If you want to know how to do this kind of problems, you can check out my videos. There are a bunch of videos on my playlist about this. And let's look at the next one. So this is linear substitution. Linear substitution. Now let's look at the next one. Here we have y dy plus x square e power 2x cube plus y square dx is equal to 0. This is a separable differential equation. This is not obvious. Now let's see how it's separable. Okay, y dy. So here y dy y square dx, in separable equation we have to bring x and y terms together, right? So like not x together, we have to separate y terms one side and x terms to the other side. So here the thing is, whenever you have e power multiplying, if you remember, when you have x square times x power 4, that's equal to x power 6. We are adding, right? When you have power multiplication, that's addition. That's what we have to do. This e power 2x cube plus y square can be separated as multiplication. In that way, we can make this one a separable. Now let's do that. Here this is going to be y dy plus x square e power 2x cube, and this plus y square, we can separate this one as e power y square, because when you multiply, the power adds. That's how we got the addition. So that's dx equal to 0. Now in separable, we have to separate x to the one side and y to the other side. So in order to do that, I move this whole things to the other side, or you can move this one to that side. In that way, that will be much easier. So this is going to be x square e power 2x cube and e power y square dx, and I move this y dy to the other side, so that's going to be negative y dy. And also in separable, we just have to have y terms in the one side and x terms in the other side. Here we have e power y square in this side, so we have to move this one to the other side. So this is going to be x square e power 2x cube dx, and if I move this e power y square to this side, this is going to be what? This is going to be negative y e power negative y square dy. Okay, so in that way, this is now a separable differential equation. Now let's go ahead and look at the next one. Here we have x dy, that's equal to xy square minus 1 plus xy dx. Now this is a Bernoulli's differential equation, and if you remember, as I mentioned before, the Bernoulli's differential equation pattern will look like this. We will have a linear differential equation pattern, and that one at the end we will have a multiplication of y power that's not equal to 0 or 1. Now let's go ahead and look at this one. This is going to be dy by dx. This is the general pattern of linear differential equation. That is dy by dx plus p of x, a function of x, multiplies y. That's equal to another function of x. So this is a linear first order differential equation. But in Bernoulli's we will have a y power something that's not equal to 1 or 0 or 1. Okay. Now let's see whether we get something like that. Here we have x dy. So first we have to bring a dy by dx. So I move this dx to this side. So this is going to be dy by dx. And also I move this x to the other side. So this is going to be x y square divided by x minus 1 plus x y divided by x. Okay, so here which one, like 1 plus x whole thing multiplied by y. Now in linear we have to have a function of x multiplied by y, so we have to move one of this thing which is a function of x multiplied by y. Which one is suitable? If you look at this one, here we have y power 2. We cannot have y power 2 in this side, right? So y power 1 is this one. So this is the one we are going to bring to this side. If we bring to this side, this is going to be dy by dx plus 1 plus x multiplied by y divided by x, and here x and x cancels each other. We will get y 1 times y square. From this one you can see this is without this y square, this is a linear first order differential equation. Because of this y square, this is a Bernoulli's differential equation. Okay, and that's how we find out whether a equation is Bernoulli's or not. Now let's look at the next one. Here we have, this is an exact differential equation. As I mentioned before, there are two different ways you can find an exact, like two different standard form. First one is m of x comma y multiplied by dx plus n of x comma y multiplied by dy, that will be equal to 0. Or in another way you will have something like this. You will have m of x comma y dx, not dx, without dx, m of x comma y plus n of x comma y, and also you will have dy by dx, that's equal to 0. There are two ways you will look at this one, but here the important thing is we have to figure out which one is m of x comma y and which one is n of x comma y. And after you find out which one is m of x comma y, n of x comma y, you have to take the derivative of m of x comma y with respect to y. So this should be my. So you have to take the partial derivative of m with respect to y, and also you have to take the partial derivative of n with respect to x and see whether these two are equal. If these two are equal, this is exact, otherwise it's not exact. Okay, now let's go ahead and see whether it's exact or not. First we have to bring this one into one of these patterns. Now let's see which one is easy. Okay, it seems like this dy by the second pattern is easy because we already have a dy by dx, so we can bring into this pattern, the second pattern. Now let's go ahead and do this one. Here we have dy by dx, and if I multiply this y times 1 minus x square, this is going to be y times 1 minus x square times dy by dx. Okay, and in the other side we have xy square minus tan x, and also I can directly bring all of them. So this is going to be minus xy square and plus tan x, that's equal to 0. Now from this one you can figure out which one is m of x comma y. N of x comma y is the term that's multiplied dy by dx. So here dy by dx is with this one, right? This is our n of x comma y. And what is the other term is m of x comma y. So this is our term of m of x comma y. Now after we find out m of x comma y and n of x comma y, we have to take the partial derivative of m with respect to y and partial derivative of n with respect to x and compare each other, and these two must be equal in order to be exact. Okay, now let's go ahead and take the derivative of this n with respect to x and see what we get. So if we take n with respect to x, we treat y as a constant. So this is going to be what? Here we will have negative 2x because we treat, okay, first before go ahead and do that, let's multiply this y outside. Because this y is outside of the bracket, first you multiply this one to avoid any confusion. Okay, So if you multiply this y with 1, that's going to be just y. And if you multiply this y with negative x square, this is going to be negative yx square. So let's write that one down right here, negative yx square. Now if you take the derivative of this one with respect to x, you treat y as a constant. So the first one is going to become 0. And if you do for the second one, this is going to be what? Negative 2xy. Okay. Now let's go ahead and look at the m of x comma y. We have to take the derivative of this m with respect to y. So we treat x as a constant. So this here we have y square, that's going to become 2y multiplied by this x, and also we have to include this negative one, negative sign, because in the standard pattern this is positive. So if it's negative, mean this negative also included in the function. So this means here we are going to have negative 2xy, and this tan x is going to become 0, because when you take the derivative of m with respect to y, we treat x as a constant. So this is going to become 0. Here we have equal, like we have both of them are equal, therefore this is an exact differential equation. Okay, now let's look at the next one. This is a homogeneous differential equation. Now this is not very obvious when you try to solve this one, like whenever you have round something like this, that's the tricky part. Now let's see how to make the, like in homogeneous, what we have to have all the powers should be equal, right? Now let's see whether these powers are equal. Here we have dy by dx and this y power 1. So the rest of them also has to be power 1 in order to be homogeneous. So if I multiply this x to both of them, this is going to be what? X plus x ln of y minus x ln of x. So this is what makes this one confusion, because we have x and also we have a ln of y. So this is what makes this one confusion. But the tricky part is whenever we have ln subtracting, it's equivalent to division. So this is going to be y divided by x plus x, and ln, instead of y minus x, we can write it as y over x. So in that way, power 1 and 1 cancels each other. This is going to be just power 0. So all of them are power 1, right? We have equal powers. It means this is a homogeneous differential equation. And that's how we find out the differential equation pattern and the type of differential equation. Okay, I hope this helps. Thanks for watching, and if you are trying to learn differential equations, there are a bunch of videos in my playlist. I hope you guys watch that too, and don't forget to subscribe. See you next time.